Alright, this is Honors Algebra, Chapter 2, Section 1, Intro to Inductive Reasoning and uh, Conditional Statements. Alright, so the inductive reasoning is actually just a way of coming into a conclusion based off of patterns, but it's sort of an informal conclusion. It's a conclusion based off of recognizing patterns, but we didn't really prove anything. The first definition the book gives is that of a conjecture. And a conjecture is you can give it as an unproven statement. So you look at a pattern and you're saying, hey, okay, I recognize that something's happening, and then you just state it. That's your conjecture, but you didn't really prove it. You just recognized it. Or we can think of it as, I would say, an educated guess based off the pattern. Then they talk about inductive reasoning, and inductive reasoning is looking at a pattern or a scenario and making a conjecture or an improvement statement or an educated guess off of the scenario. So conjecture and improvement statement, or you could think of it as educated guess. Inductive reasoning, looking at a pattern and making a conjecture or an educated guess based off of the evidence or the patterns that you see. And then the book gives you a bunch of patterns and scenarios, but I'm not going to really get into that because I'm pretty sure you guys can recognize some patterns. Then they talk about something called a counterexample. And a counterexample is a specific case where the conjecture is false. So a counterexample is finding some type of evidence or some type of scenario in which whatever the initial conjecture is, the educated guess is wrong, trying to prove it false. So the one, I'll do the book's one. The one that the book gives here, it says that the sum of two numbers is always greater than the larger number. So if we do 2 plus 5 equals 7, 7 is the sum. And then 5 would be the larger number. 5 would be the larger number. And in this case, the sum is greater than the larger number. So that works. Can we think of a scenario where that doesn't work? And that scenario is when the numbers are negative. So if we have negative 2 plus negative 5, we get negative 7. Well, which one's the larger number? Larger number here is negative 2. And negative 2 should be larger than this the sum should be larger than the negative number, so we have negative 7. And then here's negative 2. And guess what? Negative 7 is not larger than negative 2, so that's false. So we found the counterexample. This would be the counterexample. Some statement or some evidence that you can find to prove the conjecture false. Example 6 is just asking you to recognize a graph to fit some type of conjecture. Again, you guys know how to do that. This is not a particularly difficult section in terms of looking at the patterns and seeing what's going on. Example 5 says to find a counterexample of the following conjecture. The value of x squared is always greater than the value of x. The value of x squared is always greater than the value of x. Can we find a scenario when that's not the case? So this says x squared will always be greater than x. Can I think of a number where that's not the case? The number that pops in my brain is 0. So if I square 0, I'm basically 0 times 0, so 0 wouldn't be greater than 0. 0 is equal to 0. So that doesn't work. We just found a counterexample. Alright, so that's that section. Recognizing patterns, and then you'll be asked to find some type of counterexamples to various conjectures. Alright, so this is what we're going to really focus the attention on: conditional statements. A conditional statement is a logical statement. This is geometry. We're doing all logic stuff. That has two parts. It has a hypothesis and it has a conclusion. It has a hypothesis and it has a conclusion. A conditional statement is a logical statement that has a hypothesis and it has a conclusion. It is also written in the form of if and then. These are going to be if-then statements. Okay? Anything after the if is the hypothesis. Anything after the if is the hypothesis. Anything after the then statement, or the word then, is your conclusion. Anything after the if is your hypothesis. Anything after then is your conclusion of your conditional statement. Alright, conditional statement. Logical statement has two parts, a hypothesis and a conclusion, and it is written in if-then form. Anything after if is your hypothesis. Anything after then is your conclusion. The first conditional statement of the year, congratulations, is this sentence right here. If it is raining, then there are clouds in the sky. Notice there's usually a comma after the if statement, separating them from the then statement. The hypothesis is it is raining. The conclusion is there are clouds in the sky. We don't usually put the if and the then in the actual writing what those things are. It's going to be anything after the if and anything after the then. That's the hypothesis or the conclusion. So we don't actually use the word if and then in it. It's what the phrase is afterwards. So the hypothesis is it is raining, and the conclusion is the sky. There are clouds in the sky. So they give us a scenario, and they want us to write these guys in a form of if-then statement. And we have all birds have two feathers. So usually, or have feathers. Usually, when we have a sentence like this and we're asked to sort of put it in a conditional statement, it's always it's usually the phrase after the verb. So we have this sentence, they want us to write it as a conditional. The verb is have. And I know it's like, this is math class, not English class. The verb is have, right? It's usually anything after the verb is usually. I'm going to put a usually here. Anything after the verb is the conclusion. Usually. So in this case, birds would be our hypothesis, and then feathers would be our conclusion, or it has feathers. So when we write this in an if-then statement, or in our conditional statement, it would be if and a bird is an animal, right? So if an animal is a bird, comma, then it has feathers. If an animal is a bird, then it has feathers. That would turn that sentence into a conditional statement. Usually anything after the verb tends to be the conclusion, and your hypothesis is sort of if you want to break it down to like subject and predicate, usually the subject is your hypothesis and the predicate is your conclusion. Okay, two angles are supplementary if they are a linear pair. What's good about this one is that they already have it broken up. Remember, anything after if, and in the sentence itself it has the if statement, so that's nice. So two angles are supplementary, and I'm going to shorthand it, if they are linear pair. Alright, two angles are supplementary if they are a linear pair. Since we have the if statement kind of right there already, well, I wouldn't call that, well, I wouldn't call that the conclusion, but the book says another thing. So I'm not going to argue with the book. But according to the book, if two angles are supplementary, then they are a linear pair. Okay. You can turn all of these into biconditionals. Not biconditional, to conditional statements. So let's look at a few of these. All angles are right angles. All angles are right angles. So when we do all angles are right angles, we say if an angle, all 90 degrees angles, I'm sorry. If an angle is 90 degrees, then they are right angles. If an angle is 90 degrees, then actually it is a right angle. Alright, that's one conditional statement. The other one here says 2x plus 1 equals 7 because x equals negative 3. So we can say if 2x plus 7 equals 1, then x equals negative 3. If 2x plus 7 equals 1, then x is negative 3. So that's the other one. Third one, when n equals 9, n squared equals 81. So we can say if n equals 9, then n squared equals 81. And this one says tourists at the Alamo are in Texas. So we can say for this one, if a tourist is at the Alamo, then they are in Texas. Okay. Negation. Negation is the opposite of the original statement. Um, so we have statement number one. In this case, statement number one says that the ball is red. Okay. The negation of that is the ball is not red. If the ball is red, then the negation, I think of it as a negative, is the ball is not red. And we have another scenario where we have the statement as the ball is not red. The cat is not black. That is our initial statement. The negation of that is that the cat is black. So when you think of the negation, we think of it as an opposite statement. If something is, then the opposite of is that is it's not. If something is not, then the opposite of is not is that something is is. Something is. Or so when we think about negation, we think about opposite statement. So it's an opposite statement to the original statement. Opposite statement to the original statement. Okay. When we talk about other words, we could talk about a few things about conditional statements. We can have a conditional statement, and we can have a conditional statement that's false. And there's ways to do these conditional statements. Uh, and in order to prove something false, we just have to give a counterexample. So before we get to proving conditional statements true or false and counterexamples, we have to find out the various ways of doing a conditional statement. So we have something called the converse, not the shoes. The converse uh, uh, switches the hypothesis and the conclusion. All right. The converse switches the initial. So we had an initial hypothesis and conclusion. The converse switches those two, and what was once the hypothesis is now the conclusion, and what was once the conclusion is now the hypothesis. Then we have something called the inverse. And the inverse is a conditional statement that negates both the hypothesis and conclusion. So inverse negates, we talked about what a negation is, so not this or not that. Negates the hypothesis and conclusion. And then we have the inverse. I mean, not the inverse, the contrapositive. And the contrapositive does both. It does both. So think of the contrapositive as the converse and the inverse together. So it switches the hypothesis and conclusion. And put it hypothesis, H for hypothesis, and C for conclusion. Switches the hypothesis and conclusion, and it negates the hypothesis and conclusion. It switches the hypothesis and conclusion, and it negates the hypothesis and conclusion. It does both. So we have the regular conditional statement, your if then. Then we have the converse, which switches the hypothesis and the conclusion. Then you have your inverse that negates the hypothesis and conclusion. And you have your contrapositive that does both. It switches the hypothesis and conclusion, and it negates after it switches the hypothesis and conclusion. So let's look at what the book has. So the book has this initial conditional statement. An initial conditional statement is if. So this is the conditional. This is what we start off with. If the measurement of angle A is equal to 99 degrees, then it is obtuse. Okay? So when we look at this, if the measurement of angle A is 99 degrees and is obtuse, we know that 99 degrees is obtuse. So this conditional statement is true. And I can't think of a counter example to make that false. So this is true. Now let's talk about the converse. And remember the converse switches the hypothesis and conclusion. So the converse is going to be if A is obtuse, then the measure of angle A is 99 degrees. If the angle is obtuse, then the measure of angle A is 99 degrees. This is false. And the reason why this is false is we need a counterexample, right? So can I think of an obtuse angle that's not 99 degrees? Well, yes, right? What if it was 100 degrees? So if angle A is obtuse, then it can't just be 99. It can be a whole bunch of angles. So that's false. And this 100 degrees is my counterexample. Okay. So then we also have the inverse. And the inverse says, remember the inverse is the negation. So if the measure of angle A is not 99 degrees, then it is not obtuse. Okay, well, this is also false. And it's false because can I think of an angle that's not 99 degrees and that's obtuse? Absolutely, we'll use the same 100 degrees. That's my counterexample. Right? If I have an angle that's not 99 degrees, 100 is definitely not 99 degrees, then it's not obtuse. Well, yeah, it is obtuse still. So we've proven a situation where the hypothesis is true, but the uh, conclusion is false. So that's what a counterexample does. Even though it has the same hypothesis, we come to a different conclusion. All right, so let me erase the converse part because I am out of space. Hopefully I have enough space for the... Okay. And the last one we have is the contrapositive. And a contrapositive negates both the hypothesis and conclusion and it switches it. So we're going to switch it and we're going to say if A, the angle A is not obtuse, then the measure of angle A is not 99 degrees. So this is true, and it's true because can I think of an angle that's not obtuse? Yeah, I can think of an angle that's not obtuse. 80. 80 is not obtuse, and 80 is not 99 degrees. And I'm never going to think of an angle that's not obtuse that will be 99 degrees. So that's going to be true. When you negate and flip the conditional, so when you do the contrapositive of the conditional, the contrapositive will be true and the conditional will always be true when you negate them both. They're equivalent statements. They're the same. The contrapositive and the conditional, if they're both true, they're equivalent statements. And they will always be true. By the way, when you do converse and inverse, we're going to get to that in a second. They don't always have to be false. So there's going to be scenarios where they're all true, and then that's a unique situation. All right. Okay. So let's look at a couple examples. So we have if a dog is a Great Dane, this is the conditional. Okay. All right. So if a dog is a, I'm going to put GD for Great Dane because I ain't trying to write down that out, then it is large. So that's absolutely true. Great Danes are some big old dogs. So we're going to call that true. And then I can't think of a condition where I have a dog that's a Great Dane and is small. The converse would be if it is large, if it is large, then it is a Great Dane. I guess you would say if a dog is large. If a dog is large, I can't say it. It would be a dog. So I should have switched that around. If the dog is large, then it is a Great Dane. This is false because we can think of lots of dogs that are big. That's not a Great Dane. Um, and B, large. So then we have the inverse. And the inverse would be if a dog is not a Great Dane, then it is not large. That's also false. We can think of a dog that's not a Great Dane that is large. And then we have the contrapositive. And that one is if a dog is not large, then it's not a Great Dane. This is true. I can't think of a dog that is small that's a Great Dane. So this is true. Alright, so if a dog is a Great Dane, then it is large. The converse, if it is large, then it's a Great Dane. That's false because I could think of a large dog that's not a Great Dane. A dog is not a Great Dane, then it's not large. Again, I could think of a dog that's not a Great Dane, but it's still large. And then the contrapositive, if a dog is not large, then it's not a Great Dane. I can't think of a small dog that's a Great Dane. Therefore, that's true. I'm not going to do the second one. So, equivalent statements. When the conditional and its contrapositive are both true or false, similarly, the converse and the inverse of a conditional statement are either both true or false. The pairs of statements are called equivalent statements. In general, when two statements are both true or both false, they are equivalent statements. When the conditional and its contrapositive are either both true or both false, or when the converse and the inverse of a conditional statement are either both true or both false, the pair of statements are called equivalent statements. So in this case with the Great Dane, we have the conditional and we have the contrapositive, and they're both true. Since the conditional and the contrapositive are both true, then we can say that they're equivalent. Here, the converse and the inverse are also both true. And since the converse and the inverse are both true, we can also say that they are equivalent. They're the same statement, they're just sort of written in a different way. Conditional, contrapositives. So when the conditional and contrapositives are the same, are both true or false, or when the inverse and converse are either both true or false. Then they are equivalent statements. Okay. Conditional contrapositive have to both either be true or both either be false. The inverse converse have to both be either true or both either be false. If that's the case, then we have equivalent statements. So when you have a situation where they're equivalent statements, it doesn't really matter which one is your hypothesis or which one is your conclusion. So when we talk about a definition of perpendicular lines, by the way, what is a perpendicular line? Well, there's two ways to write it. So if we do it in the form of an if-then, if two lines intersect to form a right angle, then they are perpendicular lines. We can also write the converse, and the converse is also true in this statement. So we can also say for perpendicular lines that if two lines are perpendicular, then they form a right angle, or they intersect to form a right angle. Okay. So those are the two ones. So this is the hypothesis, and this is the converse, or the conditional, and this is the converse. There's a symbol, right? So if we look at the situation, we have a line, and it is line L. We have another line, line M, and it forms a 90-degree angle. And we can say that line L is perpendicular to line M. So this symbol here, instead of writing perpendicular, this means perpendicular. Because don't nobody want to write perpendicular. Okay, so that symbol means perpendicular. So we have a bunch of scenarios down here, and we've learned some definitions by now, and they want us to know if these guys are true or false depending on the evidence and what we've learned. So it says angle JMF and angle FMG. So JMF and FMG, are they supplementary? And the answer is yes, they are. So angle JMF and angle FMG, they are supplementary, but they're supplementary because they are linear pairs. And if you notice the definitions in the book, they are they all are in the form of conditional statements. So we would say if two angles form a linear pair, then they're supplementary angles. So this one would be true because of definition of linear pairs. So the next one is point M is the midpoint of FH. Uh, oh my god, the stylus sucks. I would say false. And it's false because we don't have enough information on the picture to tell me that it is true or false. I just don't have enough. So I can't say that it's true. So it's false. Angle FMF, JMF, and HMG are vertical angles. JMF. That's not what I did. And angle HMG are vertical angles. This is true because we have a pair of opposite rays that form the angle, so that's true. And then the last one, FH is perpendicular to FH is perpendicular to JG. That's false. We don't have any indication that they are. There's no box or anything. Plus, you can even look at it and tell that's not the case. All right. The last thing we have is something called a biconditional statement. And a biconditional statement is a statement where the conditional statement and the converse are both true. I repeat, and that's what we did with the definition of perpendicular lines. The conditional and the converse are both true. So that's called a biconditional. So biconditional, the conditional is true, and the converse, kiss my converse. For those who don't understand, that's an old movie reference. Go watch The Last Dragon if you ever never heard of it before. Converse is also true. So when they're both true, we have a biconditional. And instead of saying if then, we use the phrase if and only if. So it's saying in terms of the perpendicular lines, and we have it right here. So with the perpendicular line, we said if two lines intersect to form a right angle, then they're perpendicular. Then we said the converse is true. If two lines are perpendicular and they intersect to form a right angle, we can take out the if then, and we're going to put if and only if in the middle. And that would be two lines are perpendicular. Two lines are perpendicular. If and only if. They intersect to form 90 degree. A right angle. Not 90 degrees. That's a mess. Alright. Okay, so that's that section. So it's a lot of definition heavy, and it's stuff you guys not really used to seeing before. Um, but it's our introduction to proofs. So I hope you guys have a great rest of your day.